Burn like a pro.
Hey there. You do something about 22,000 times a day without even thinking about it, breathing. But have you ever actually stopped to wonder, what is this stuff we're pulling into our lungs? Today, we're going to break down the anatomy of the very air around us. I mean, really, let that sink in. We just call it air and kind of think oxygen, right? But is that the whole story? Oh, not even close. The actual blueprint for our atmosphere is way more interesting than you'd think. Let's dive in. All right, so here it is. This is basically the recipe for dry air. And what's wild is how consistent and predictable this mixture is. What we call air is really this cocktail of different gases, and the main ingredient is probably going to surprise you. Okay, get ready for this, because it's the first big shocker. The number one ingredient in the air you're breathing right now, it's not oxygen. Nope, it's nitrogen, a massive 78%. It's this silent, invisible giant in every single breath you take. Next up, we've got the one we all know and love, oxygen. It makes up about 21%. So yeah, think about that for a second. Only about a fifth of every breath you take is the stuff that actually, keeps you alive and kicking. So that leaves this tiny little 1% sliver. Doesn't seem like much, does it? But trust me, there's some really interesting stuff packed into this last little bit. So, what's hiding in there? All right, let's zoom in on that final 1%. Almost all of it, like 0.95%, is made up of these things called noble gases, mostly argon. They're super chill, they don't really react with much. And the rest? That's where you find a tiny bit of carbon dioxide and a few other trace elements. Okay, so now we know the recipe, but how in the world do you unmix it? How do you pull apart this invisible soup of gases to get pure oxygen or pure nitrogen when you need it? Well, we do it with this really clever two-step process. The whole thing works because of some seriously cool physics, basically forcing the air through some extreme temperature changes, from gas to liquid and right back to gas again. So here's how this separation engine actually works. Step 1 is called liquefaction. We make the air so incredibly cold that it actually turns into a liquid. Then comes step 2, fractional distillation. That's when we slowly and very carefully start to warm it back up. And this is where the real magic happens. The whole thing is possible because of a process called fractional distillation. Just think of it like this. Every gas in that liquid air has its own unique escape temperature, its own personal boiling point. So as we turn up the heat, each gas is going to boil off at a very specific moment. So picture this. We've got our liquid air, and we start to gently warm it up. The gases start to separate themselves out perfectly. The very first one to boil away is nitrogen, at a mind-bogglingly cold minus 196 degrees Celsius. We collect that. Next to go is argon at minus 186. And finally, the last one left is oxygen, which boils at minus 183. We just capture them one by one as they turn back into a gas. All right, that is a lot of work, right? We're talking about some seriously extreme temperatures, which brings up a pretty obvious question. Why? Why on earth do we even bother going through all that trouble? Oh, the payoff is absolutely huge. Take that pure oxygen we just separated out. In hospitals, it is literally a lifesaver for people who are having trouble breathing. And in the industrial world, you mix it with another gas, acetylene, and you get torches so hot they can slice right through solid steel. This brings us full circle to the last piece of our puzzle. We have this blueprint that says air is 21% oxygen. We have a way to pull it out. But how did we even figure that number out to begin with? How do you prove it? Well, the proof comes from this incredibly simple, just elegant little chemistry experiment. It uses a piece of phosphorus to let us literally see and measure how much oxygen is in the air. Okay, check this out. It's so cool. First, you trap some air in a tube over a dish of water. Then, you heat up a tiny piece of phosphorus inside that tube. Now here's the trick. Phosphorus is super picky. It only reacts with oxygen, so it burns up and completely removes only the oxygen from the air in the tube. As that oxygen disappears, it creates a vacuum, and the water from the dish gets sucked up to fill the space. And guess what? The water rises to fill, you guessed it, almost exactly 21% of the tube. It's the perfect visual proof. And just like that, we've closed the loop. We started by identifying what's in the air. Then we figured out how to separate it. We saw the incredible ways we can apply it. And finally, we just saw how we can verify that our original blueprint was right all along. So the next time you take a big, deep breath, you'll know exactly what you're pulling in: a whole lot of nitrogen, that vital hit of oxygen, and a little bit of argon. But it does make you wonder, right? What other cool stuff could be hiding out in that last mysterious 1%?